pneumatic cylinder, S, are mechanical devices which use the power of compressed gas to produce a force in a reciprocating linear motion. Like hydraulic cylinders, something forces a piston to move in the desired direction. The piston is a disc or cylinder, and the piston rod transfers the force it develops to the object to be moved. Engineers sometimes prefer to use pneumatics because they are quieter, cleaner, and do not require large amounts of space for fluid storage. Because the operating fluid is a gas, leakage from a pneumatic cylinder will not drip out and contaminate the surroundings, making pneumatics more desirable where cleanliness is a requirement. For example, in the mechanical puppets of the Disney Tiki Room, pneumatics are used to prevent fluid from dripping onto people below the puppets. Operation General once actuated, compressed air enters into the tube at one end of the piston and, hence, imparts force on the piston. Consequently, the piston becomes displaced. Compressibility of gases one major issue engineers come across working with pneumatic cylinders has to do with the compressibility of a gas. Many studies have been completed on how the precision of a pneumatic cylinder can be affected as the load acting on the cylinder tries to further compress the gas used. Under a vertical load, a case where the cylinder takes on the full load, the precision of the cylinder is affected the most. A study at the National Cheng Kung University in Taiwan concluded that the accuracy is about a plus or minus 30 nanometers, which is still within a satisfactory range but shows that the compressibility of air has an effect on the system. Failsafe mechanisms Pneumatic systems are often found in settings where even rare and brief system failure is unacceptable. In such situations, locks can sometimes serve as a safety mechanism in case of loss of air supply and, thus remedy or abate any damage arising in such a situation. Leakage of air from the input or output reduces the pressure and so the desired output. Types: although pneumatic cylinders will vary in appearance, size and function, they generally fall into one of the specific categories shown below. However, there are also numerous other types of pneumatic cylinder available, many of which are designed to fulfill specific and specialized functions. Single-acting cylinders Single-acting cylinders use the pressure imparted by compressed air to create a driving force in one direction, and a spring to return to the home position. More often than not, this type of cylinder has limited extension due to the space the compressed spring takes up. Another downside to sacks is that part of the force produced by the cylinder is lost as it tries to push against the spring. Double-acting cylinders Double-acting cylinders use the force of air to move in both extend and retract strokes. They have two ports to allow air in, one for outstroke and one for instroke. Stroke length for this design is not limited, however, the piston rod is more vulnerable to buckling and bending. Additional calculations should be performed as well. Multi-stage, telescoping cylinders Telescoping cylinders, also known as telescopic cylinders, can be either single or double-acting. The telescoping cylinder incorporates a piston rod nested within a series of hollow stages of increasing diameter. Upon actuation, the piston rod and each succeeding stage telescopes out as a segmented piston. The main benefit of this design is the allowance for a notably longer stroke than would be achieved with a single-stage cylinder of the same collapsed length. One cited drawback to telescoping cylinders is the increased potential for piston flexion due to the segmented piston design. Consequently, telescoping cylinders are primarily utilized in applications where the piston bears minimal side loading. Other types Although sacks and DACs are the most common types of pneumatic cylinder, the following types are not particularly rare: through-rod air cylinders. Piston rod extends through both sides of the cylinder, allowing for equal forces and speeds on either side. Cushion-end air cylinders Cylinders with regulated air exhaust to avoid impacts between the piston rod and the cylinder end cover. Rotary air cylinders Actuators that use air to impart a rotary motion. Rodless air cylinders These have no piston rod. They are actuators that use a mechanical or magnetic coupling to impart force, typically to a table or other body that moves along the length of the cylinder body, but does not extend beyond it. Tandem air cylinder Two cylinders are assembled in series in order to double the force output. impact air cylinder, high-velocity cylinders with specially designed end covers that withstand the impact of extending or retracting piston rods. Rodless cylinders. Some rodless types have a slot in the wall of the cylinder that is closed off for much of its length by two flexible metal sealing bands. The inner one prevents air from escaping, while the outer one protects the slot and inner band. The piston is actually a pair of them, part of a comparatively long assembly. They seal to the bore and inner band at both ends of the assembly. Between the individual pistons, however, are camming surfaces that peel off the bands as the whole sliding assembly moves toward the sealed volume, and replace them as the assembly moves away from the other end. Between the camming surfaces is part of the moving assembly that protrudes through the slot to move the load. Of course, this means that the region where the sealing bands are not in contact is at atmospheric pressure. Another type has cables extending from both ends of the cylinder. The cables are jacketed in plastic, which provides a smooth surface that permits sealing the cables where they pass through the ends of the cylinder. Of course, a single cable has to be kept in tension. Still others have magnets inside the cylinder, part of the piston assembly, that pull along magnets outside the cylinder wall. The latter are carried by the actuator that moves the load. The cylinder wall is thin, to ensure that the inner and outer magnets are near each other. Multiple modern high-flux magnet groups transmit force without disengaging or excessive resilience. Design construction depending on the job specification, there are multiple forms of body constructions available. Tyrod cylinders, the most common cylinder constructions that can be used in many types of loads, has been proven to be the safest form. Flange-type cylinders, fixed flanges are added to the ends of cylinder, however, this form of construction is more common in hydraulic cylinder construction. One-piece welded cylinders, ends are welded or crimped to the tube. This form is inexpensive but makes the cylinder non-serviceable. Threaded end cylinders, ends are screwed onto the tube body. The reduction of material can weaken the tube and may introduce thread concentricity problems to the system. Material upon job specification, the material may be chosen. Material range from nickel-plated brass to aluminum, and even steel and stainless steel. Depending on the level of loads, humidity, temperature, and stroke length specified, the appropriate material may be selected. Mounts depending on the location of the application and machinability, there exist different kinds of mounts for attaching pneumatic cylinders. Sizes air cylinders are available in a variety of sizes and can typically range from a small 2.5 mm air cylinder, which might be used for picking up a small transistor or other electronic component, to 400 mm diameter air cylinders which would impart enough force to lift a car. Some pneumatic cylinders reach 1000 mm in diameter, and are used in place of hydraulic cylinders for special circumstances where leaking hydraulic oil could impose an extreme hazard. Pressure, radius, area and force relationships. Rod stresses due to the forces acting on the cylinder, the piston rod is the most stressed component and is to be designed to withstand high amounts of bending, tensile and compressive forces. Depending on how long the piston rod is, stresses can be calculated differently. If the rod's length is less than 10 times the diameter, then it may be treated as a rigid body which has compressive or tensile forces acting on it. In which case the relationship is: where is the compressive or tensile force, is the cross-sectional area of the piston rod, is the stress. However, if the length of the rod exceeds the 10 times the value of the diameter, then the rod needs to be treated as a column and buckling needs to be calculated as well. In-stroke and outstroke although the diameter of the piston and the force exerted by a cylinder are related, they are not directly proportional to one another. Additionally, the typical mathematical relationship between the two assumes that the air supplied does not become saturated. Due to the effective cross-sectional area reduced by the area of the piston rod, the in-stroke force is less than the outstroke force when both are powered pneumatically and by same supply of compressed gas. The relationship between the force, radius, and pressure can be derived from simple distributed load equation. Where is the resultant force, is the pressure or distributed load on the surface, is the effective cross-sectional area the load is acting on. Outstroke, using the distributed load equation provided that can be replaced with area of the piston surface where the pressure is acting on. Where, represents the resultant force, represents the radius of the piston, is pi, approximately equal to 3.14159. In-stroke, on in-stroke, the same relationship between force exerted, pressure and effective cross-sectional area applies as discussed above for outstroke. However, since the cross-sectional area is less than the piston area, the relationship between force, pressure and radius is different. The calculation isn't more complicated though, since the effective cross-sectional area is merely that of the piston surface minus the cross-sectional area of the piston rod. For in-stroke, therefore, the relationship between force exerted, pressure, radius of the piston, and radius of the piston rod, is as follows. Where, represents the resultant force, represents the radius of the piston, represents the radius of the piston rod, is pi, approximately equal to 3.14159. See also, fluid dynamics, fluid power, hydraulics, pneumatic motor, pneumatics, tubular linear motor. References, ABCDEFG, 1, Majumdar, S. A Pneumatics System, Principles and Maintenance. New Delhi, Tata McGraw-Hill. Cheng, Chi Neng Design and Control for the Pneumatic Cylinder Precision Positioning Under Vertical Loading, Ergo Help Pneumatics, EHTC Telescoping Cylinders, 2, diagrams that show the principle are on pages 6 and 7. Only one piston is shown in the cutaway. The other is hidden. It is symmetrical, but reversed. Parker-Origa also makes similar cylinders with sealing bands. Pneumatic actuators. Pneumatic. Retrieved May 3, 2011. Pneumatic cylinders, North America. Parker Hannifin. Retrieved May 3, 2011. Hibula, R.C. Engineering Mechanics, Statics. New Jersey, Pearson Prentice Hall. ISBN 0-13-221500-4. External links, Special Types of Cylinders, www.pneumatics B, Checklist for Pneumatic, www.Dielton Group in.